I am very sorry. I will talk about a subject which I developed with Tomasz Lekszycki, who left us Friday, 8th of September for an aneurysm caused without symptoms, caused by atherosclerosis. Tomek, this is the most smiling face of Tomek. While having Skype meetings, very often I believe that the screen was frozen. However, he was one of the most clever expert in variational principles and mechanics and biomechanics whom I ever met, and this is, I said this also when he was alive. Many ideas I will tell you were a collaboration with him, so I think that the video recorded, this video recorded presentation I will send to Warsaw, and this will be my contribution to a more general set of tributes they are doing for him. Okay, so do you know that vertebrates are in this world since more than 500 million years? So they managed to develop, using natural selection, a very complex structure of bones. And you have weight-bearing bones and protective bones. So we will start focusing to weight-bearing bones, because for these bones you have a specific mechanism of growth and remodeling about which we'll talk, and which needs a modeling. And as I wanted to do in my life mathematical modeling, when I found this problem, I decided it was rather interesting. The adaptive process of bone remodeling depends on the frequency and the number of cycles of the mechanical load. And I must thank Ivan that stopped his presentation, allowing me to talk about this subject, which we developed together with him under the pressure of Tomek, and he was invited here, so it's a pity he cannot hear what we managed to do. The mechanical loads acting on the skeleton belong to two categories. One, low frequency range and high amplitude, 1.5 Hertz, 2,000, 3,000 microstrains, walking. Okay? So we are not surprised that walking is acting on sending a signal to a bone telling him it grow. Okay? But you have also high frequency range and low amplitude, 10, 60 Hertz, but smaller than 50 microstrains. This is related to skeletal muscle interaction. Okay, so we will focus here on the first kind of loads. Okay, why I wanted to tell you that, of course, I needed to remind this, that vertebrates are the issue of more than 500 years, 500 millions of years of evolution. Because bone is the paradise of people who like multi-scale, multi-physics modeling. I have counted with Tomek 21 different length scales. And I must tell you that many medical doctors, biologists, have troubles in separating the length scales. Okay, and as I told you, there are many mythological beliefs about how a bone is behaving. For instance, I've never understood how somebody could conclude that a piezoelectric effect was occurring in it, measuring deformation and sending an electric message. Or I could never understand, but in this second case maybe it is my fault, how the fluid flow in canaliculi can produce a dissipated energy which could be the source of the biological stimulus about which Ivan was talking in the previous lecture. Okay, so there are so many things which are not understood and need to be understood. This is a schematic and rudimental representation of a bone tissue, and you have cortical bone tissue which is very stiff and dense. You have trabecular bone in which you have trusses. Actually, they optimize load bearings with trusses. There are different kinds of bones. All of them are being remodeled. All of them are being remodeled under the action of external loads. Here, in order to prove that I'm not senile, I will show you some results which we obtained recently to show that we can keep doing mathematics. And I will postpone, after I've shown you the results, some philosophical considerations which are of interest in the context of the present meeting. Okay? But what is interesting is that only in 1881 Wilhelm Rooks suggested that the formation and functional adaptation of trabecular architecture in bone is regulated locally by cells, governed by mechanical stimuli in a self-organizational process. Okay, so he had this idea and proved more or less in a founded way. Frost introduced, taking it from thermodynamics, his conceptual mechanostat theory. Actually, it is Lyapunov dynamical equilibrium concept, but he claims that local strains are assumed to regulate bone mass as exactly paralleling what happens to the local temperature in a room, which is regulated by a thermostat. Okay. Now the process is we try to describe here quickly. Here you have the input, physiological input, hormones and nutrients. There is a lot of mythology about hormones, but let us pretend that growth is regulated by an hormone which is diffusing in the bone tissue. Okay. Of course, if you are healthy, your input here in the regulation system is more efficient. If you are less healthy, so we could think as if we had a biological energy. Actually, with Tomasz, we tried to formalize all this process using variational principles, and we did not produce yet a paper. Then you have the mechanical stimulus which comes from osteocytes, which are osteocytes? Sensors. You have a network of sensors in the bone tissue, and these are producing our hormone depending on the measured state of deformation in the system. Okay? The mechanical stimulus tells to precursor cells, osteoblasts and osteoclasts. Greek is beautiful. Blast is producing, clast is eating. So osteoclast is producing bone, and osteoclast is eating bone. Think iconoclasty, and you remind this. Okay, and precursor cells. This is very important. The same cell can become either osteoblast or osteoclast, depending on the signal which is reaching it. Okay, these cells are filling the porous part of the tissue, so they are arriving everywhere. And when the signal tells them, they activate and they do what they have to do. When an osteoblast is fully surrounded by bone tissue, it becomes an osteocyte. And its connections with its friends around him become the network signal which is used for mechanosensing. Now, I have asked to many people, if you manage to find somebody who can answer me, I said, are osteocytes transmitting each other messages via these dendrites interconnecting them? Is an hormone diffusing? They are not answering. Okay? So I think this is already something very important to be understood. Okay. Then you have the bone tissue to which you apply mechanical loads. If the mechanical loads are strong enough, then the signal is eat, because, sorry, vice versa. If the deformation is small, it tells eat. If the signal is high, it tells build. Okay. The reason clearly is that our body wants to optimize its resources. Okay. So natural selection is actually producing a machine which is self-optimizing its own structure. And this is beautiful. Okay. Now, I did some propaganda drawings. So osteoclasts, osteoblasts, and osteocytes. So osteoblasts are building, osteoclasts are eating, osteocytes are sending messages. Okay, we said that osteoclasts are in charge of natural bone and artificial material resorption. Osteoblasts can synthesize only natural tissue. By the way, there are some scaffolds which can be eaten by osteoclasts. And these artificial materials are very clever because they can be metabolized by the cells already available in our body. And osteocytes, now this is my statement, can measure the deformation energy at a given point. Who knows what they are measuring? Okay, this is our modeling assumption. And sends a signal to other cells which start synthesizing or resorbing depending on the intensity of the collected signal. Okay?
The osteocytes, they are inside the bone?
They are inside the solid part of the bone.
But
of the
the
bone.
other, they are outside.
Sorry?
The other, the osteoclast and the... No.
As I told you, a bone is very porous.
So they are outside the...
They are outside the crystallized part of the bone, and they swim in the fluid which is inside the pores.
But the osteocytes, not.
The osteocytes are there, and they die with the bone around them. Okay.
You're saying the signal, whether to build or eat, depends on the intensity, or is it the nature of the signal? I mean,
okay. Let us say in this way, if you develop, I want to be precise epistemologically speaking, if you invent a model in which local deformation energy produces the signal which is then transmitted, you get a reasonably good prediction of what happens. But which is the true mechanism, I could not find in the literature. Please consider that in United States, okay, I am like Bersani, I forgot the name, Cohen got a professorship in biomechanics, being a mechanician of continua. He has spent his life looking for sources to give us phenomenology on which elaborating our models. And I could not find anything in his book and anywhere else. Could be my fault. But however, as I told you, somebody believes that inside, at a certain length scale, you have some caniculi, some small tubes, whose only reason for existing is to, when squeezed, to move a fluid, and this fluid is very viscous, produces dissipated energy, and gives us the message. However, what they are measuring, I believe, is the local deformation energy with a mechanism which has to be better understood. Okay. So what is important? Osteocytes are present only if natural bone is present around them. Okay? So we can suppose that osteoblasts and osteoclasts are uniformly distributed both in natural tissue and in the artificial material due to porosity, while present in natural tissue. Okay? Now, usually, you need vascularization for growing a big piece of bone, okay? But small grafts can be handled simply placing a scaffold porous. If it is not porous, forget it. I mean, nothing will happen. So you need the right porosity. In this, Tomasz was a great specialist. He could find the sources. So we know exactly which is the range of porosity allowing for the activation of osteoclasts and osteoblasts activity. Okay. Now look, this is a schematic drawing telling what happens in the problem described by Ivan before. You have natural bone, bioresorbable material. You have red are osteocytes, black are osteoclasts, yellow are osteoblasts. They send a signal, okay? But here, there is no signal. Absence of signal means eat. So the bioresorbable material is eaten, while at the boundary with the natural bone, you have a growth, okay? And if you have, it is written in French, I made a presentation in French, if you have a large value of external loads, you reconstruct the bone. This was what Tomasz was explaining me. He made also experiments on sheep's bone, okay? If instead the load, exterior load, is not big enough, then the bioresorbable material is eaten and the graft is not successful, which was a disaster in many cases. Okay, so what we can conclude is that bone structure represents an optimum balance between the costs of excessive bone mass and the cost of excessive bone fragility. We have a self-controlled system developed in every vertebrate, which is using exactly the minimum biological energy needed for keeping you working and not more. And this is the reason for which astronauts, when come back, cannot stand up, because notwithstanding heavy exercise, their bones cannot support loads. Okay? The time period is 2-3 weeks. This is enough. Okay? So our body is optimizing. Probably calcium is so precious that it wants to place it in the right position when needed. Okay? So what happens? The minimum adequate structure is achieved by adjusting the distribution of bone mass to maintain desired peak magnitude of mechanical strain within the tissue. The tissue should not be too much deformed, and arranging its microstructure in an efficient composite structure. As I told you, you have different kinds of bone, and so it is reorganizing in such a way that the right microstructure is obtained. Bone is pound for pound 4 times stronger than concrete, stronger than some steels, and more flexible. Okay, we suspect that Eiffel was designing the Eiffel Tower, copying the trabecular bone structure. Remodeling is the process in which bone is resorbed and replaced in situ by new bone. Remodeling repairs microcracks. This is another difficult problem which I would like to remark, and we are not modeling for the moment it, and replaces aged bone in a mass turnover process. Okay, it also can adjust bone strength, increasing or decreasing its mass and in turn its stiffness. Okay, now I am aware that we are doing a very brutal simplification in our modeling, and honestly I'm making the list of all simplification made. So we make no distinction depending on the type of bone structure. The effects of mechanical wear and biochemical agents probably occur at different rates and in different kind of tissues and functional parts of the skeleton. So this, we are aware of that. However, the concept of feedback control is pervasive for all weight-bearing bones. I know Tomek was a little bit like our friend Alberto. I have lost the access to his written notebooks because he didn't leave the code to his computer and his daughter could not give me his files. They are lost forever. They are protected. We had started modeling bone in linear elasticity with a full linear elastic fourth order tensor. But up to now, I can present only results in which the elasticity is treated in a simplified manner, so isotropic. I know it is rather brutal, and increases in bone mass are assumed to have direct effects on bone rigidity. So we assume that Young and Poisson moduli are depending on the mass density via a constitutive equation. This has to be improved, but I want to show you an idea, and I think we have done. And I told you that characteristic time for changes in bone rigidity is closely linked to the duration of the remodeling cycle. The minimum time over which a change in bone structure will be completed is between 100 and 120 days in a human being. So this for giving a timeline idea. Then in the literature, but we will go quickly on this, in the literature you find interesting constitutive equations for the driving force to growth, which is this simple one. You have a signal, okay? If you want, you can think about a density of an hormone in the tissue, okay? You have a reference value for the stimulus. You have the imbalance and a function, you can assume it is linear, telling you that if S is greater than S0, it grows. If S is smaller than S0, it is resolved. Or you can assume, which I think is better, an evolution equation of this kind. Okay. Then Tomek came to me and showed me some experimental evidence which proves that the local deformation energy U or the local strain is not the right quantity to calculate the stimulus. You need to know, for getting the stimulus in one point, you need to know what happens to the deformation energy in a neighborhood of the point X. And omega bar is the osteocytes density. So you need a network of sensors, the deformation energy, and a range of influence of sensor cells. And this function must be decreasing when the distance between X and Y increases. This is the reason for which I was asking to people how these cells are talking one with the other. Because I wanted to try to understand what happens with this. Okay, but the signal is transmitted instantaneously, okay, in this model. And we had a big debate about which function f was better, and we have chosen this one for a trivial reason. Numerical codes are much better if you use this. Okay, so this was a reason. Okay, then Ivan has told you that next step we wanted to, in the modeling we tried, was to including a parabolic evolution equations for stimulus. Okay, you have a source of stimulus which depends on local deformation energy. Eta is the sensor efficiency, and then you have a sink of signal which tells you something about a metabolic activity. The reason for which I like the idea of an hormone is that in the tissues we have a system for digesting hormones. So you have a way for absorbing the hormone. You need an heaviside function for avoiding problems. The signal S must be always positive. So we invented this trick, mathematically speaking. Okay. However, it is very well known that heat equation is sending a instantaneous signal at infinity. Actually, in theoretical physics, there was a violent debate about heat equation because relativity is not allowing you to send a message at an infinite distance. Okay? Cattaneo, who was professor in Rome, a pupil of Levi-Civita, proposed to add a kind of inertia. By the way, for those among you who like variational principles, parabolic equations are not variational. This one is variational. So I think it is even more elegant. So mathematics is telling you what you should do also in this context. Okay, so our idea, I want to be honest, I tried, and Ivan was following me, and we wanted to make a surprise to Tomasz. I advise not to do this. If you have an idea, you are working with somebody, call him immediately and tell him what you are doing, okay? You could be on the dying side of the story, okay? So I wanted to tell him how beautiful is this idea. You add a characteristic time here, and you get a second order hyperbolic partial differential equation with attenuation. The attenuation is here and is in S, okay? So what you get? An equation which adds the features of wave response to diffusion phenomena, okay? Very well. And now we write the correct functional adaptation rule in bone tissue. The reference density, mass density is, the derivative is evolving as a function of the stimulus times a function of the porosity. The porosity has this H has this dependence on the porosity. You have an optimal porosity, H is most active. When it is 0 or it is 1, you have no growth. And this is the main contribution, I think, of Tomasz Lekszycki to our story, because he spent 2 years for getting data to produce this result. The idea is very simple. You have an amount of surface available inside the pores. The osteoblasts and the osteoclasts are depositing there, and they start acting. So if the surface is small, they cannot act very much. So if you have a dense bone, no action. If you have no bone, no action. They have nowhere where they can deposit. And to be more precise, we introduce this A of S, which is a piecewise linear. You have a first activation energy, then you threshold, then you have a plateau in which nothing happens. So for an interval of stimuli, you don't have neither growth nor resorption, and then you have a linear signal dependence on of this coefficient on the signal. Okay, so this is the growth rule which we are using. Okay, this you have already seen, so we can go quickly beyond this. By the way, this energy has been postulated by Cohen for porous continua, and we are using this particular isotropic constitutive equation for linear elasticity. And so we are to the toy example, which needs to be developed. However, this toy example gives us a strong indication of a surprise, because we applied Cattaneo equation here with a uniform load, okay, extension test with uniform load varying over time, and initial apparent mass density normalized to the maximal one equal to 0.5, okay? And for the stimulus, we set zero flux boundary condition. So what happens inside this box depends only on what the deformation measure inside the box. By the way, the integral formulation, which I've shown you before, had many problems, because what are you doing when you are here? You are integrating in a neighborhood, you see 1/2 bone, 1/2 empty, you do not know. Here, you apply zero flux boundary condition to the heat flux. This is very similar to what you have done, and you don't have problems. So also mathematically speaking, this is very interesting. Then, here you have the history of force and its fast Fourier transform. So we are varying, you see, you have more or less constant amplitude in this range of frequency. So we are doing a test of growth, okay? And then what we do, we check what happens to the stimulus and what happens and its fast Fourier transform. And we discovered, and to be honest, this was a surprise, that Cattaneo equation introduces the selection of a certain frequency. Okay? The stimulus in the excited frequency range shows a peak at a specific frequency. So this system has a preferred external load frequency which produces a strong stimulus. So if you choose this frequency, the bone goes from 0.5 to more than 0.8 and remains stationary. So we have, I think, discovered a mathematical model which allows you to predict the selection of frequencies which is observed experimentally. Okay? If instead you choose a lower frequency, you lose mass, and if you have a higher frequency, you lose mass of the bone. So now we are motivated to start a serious numerical simulation in which we have three-dimensional bones, and we can try to discover what happens in this complex geometry, how the bone is growing under cyclic loads. Okay? Everybody who has had his broken leg knows that they place some loads with a certain frequency. And now modern physicians suggest you to walk. This is causing the bone to be healed more quickly. Okay, now why I'm telling you here, okay, and why this is interesting in the context of grafted bones. Of course, we need a scaffold made of a certain metamaterial. Okay? Now, unfortunately, Marco Miniaci is not here. I have modified the definition of metamaterials. Metamaterials are materials that may already exist in nature or that may have been invented via synthesis, for which in a given time and in a given group of scientists, there was not available mathematical effective, sorry, 2 times description, and for which this description was later found. Okay? Because bone is existing before us, and it has all features of a metamaterial, for instance. And we must mimic the properties of a bone with the scaffold. Okay. Why bioinspiration must be very useful in designing novel metamaterials? And now I went back to ancient knowledge. For this would be agreed by all that nature does nothing in vain, not labors in vain. As many people tell us that translation is betraying the original text, also thanks to Roberto Fedele, here skeptical people can read in Greek and check if this is exactly. Believe me, this is not a joke. Many times, people in the audience told me that I was forcing an ancient text to mean something else. So, okay, even if I need that Roberto is better than me, believe me, this Greek tells exactly that. Okay? But for people who are from France, I have many French friends, la nature, dans la production de ses effets, agit toujours par les voies les plus simples. Okay? Pappus proves that bioinspiration and interaction between mathematics and physics already fruitfully started during Hellenistic epoch. In the book dealing with minima, he observes that bees, before building hexagonal hives, seem to have solved an optimization problem. I'm not giving you the Greek text, believe me. In fact, among regular polygons which tile the plane, the hexagon is the one which, with the least perimeter for a given area, or equivalently, the one which allows for the use of the least amount of wax to hold a given amount of honey. This was known 3rd century before Christ. Okay? So, if we need a quick solution to a certain optimization problem, following the wiseness of Hellenistic scientists, we can see how natural selection did calculate optimal configurations. Now, I did not know that our friend who yesterday has told us that we are not yet capable to find the shape of what is the name of this bone? Even in Italian, I don't. A femur. Okay. It is clear that natural selection has chosen the lines of stress levels for building the trabeculae. And this is Wolff's law, which has been observed in 19th century. So it is clear that when our mathematics is not good enough yet, I hope we can do better, but we can use natural selection for getting suggestion. Okay. But which was the dream of Tomasz and myself, and I will try to pursue in this dream. The idea was to invent scaffolds in which the biological stimulus is propagating as it has to be, or maybe even amplified, in order to place this kind of prostheses inside bones, and these prostheses must be replaced as quickly as possible by natural bone having the correct microstructure. Okay, So having understood that you need Cattaneo equation for getting a good prediction about natural bone remodeling is a strong indication of what we have to do for developing this scientific problem. Okay? And you see, I'm not completely senile. I said what I wanted to say without reading. Okay? Now, these two pantographic structures are being built in Germany, in Freiburg, in Fraunhofer Institute, and Maximilian Stilz will talk about these things. I strongly believe that this could be very useful in the design of these prostheses. Okay, I conclude telling you that I want to avoid, I'm old enough to know that polemical remarks about contemporary scientists are not only not polite, but are also dangerous for who is talking. Okay? So, I tell you about Pliny the Elder. I think that there are many Pliny the Elder around us. Pliny the Elder was a decadent Roman who could barely read what was written in the scientific books of Hellenistic epoch. You know, there was a big problem with there was a jump between Greek and Roman culture with the collapse of Syracuse, because Syracusans were weak politically and strong scientifically. Romans were strong politically and weak scientifically. Romans won bribing the party against the tyrant of Syracuse. They opened the door. So the siege of Syracuse had 1 Greek dead, 20 Roman dead in this percentage, but Romans won. Okay? We should think about this when we think about Europe. Okay? Let us try to avoid to open our doors to enemies. Okay? Pliny, 200 years later, tried to understand Pappus' book. Okay? But he had no direct descendants via master and pupil from the Greek masters. So, critical analysis is useless for engineers. You know. He prefers a simpler one, practical explanation. Every cell is 6-sided because each side is the work of 1 leg. And bees have 6 legs. Okay? We should be aware of the dangers of excessive simplifications. Okay? So these are the references, and let us say chess to Tomasz. I will try to do some of the work without him. Okay? Thanks a lot.